Hi guys, me again, going over the different parent graphs. I know we've already gone over the quadratic or the parabola with the parent graph x squared. I'm going to do it anyway because it'll help when I talk about the square root. So if I simply plug in my x values over here into my equation y equals x squared, I'm going to get negative 2 squared, which is positive 4. Negative 1 squared, which is 1, and 0 squared, which is 0, 1 squared, which is 1, and 2 squared, which is 4. If I graph those 5, you know already those are the 5 points that I expect you to draw anytime you are doing a parabola. So always make sure you specify those 5 points. The domain here is all real numbers. The range is y is going to be greater than or equal to 0. We can generalize that by saying that y is greater than or equal to the k value as we move this around. But we're not going to do that yet. So, and this one does not have any asymptotes. Come back here are numbers that have perfect square roots, because something squared. Back to the to specifying locator point is the vertex on a parabola. And when I refer to the locator point, I'm saying what is HK. Next up, we have the square root graph. And my negative 2, negative 1, 0, 1, 2 doesn't work for a couple of reasons. Negative 2 does not have a real square root. It has an imaginary square root, which we'll talk about many chapters later. So we're not going to use, yep, there we go. We're not going to use those values, so we can't use any negatives. We're also not going to use like 0, 1, 2, 3 because what I really want, I'm going to have a square root. So what I'm going to use is 0, 1, 4, 9, and 16. 16 won't fit on our graph, so we're not going to be able to do much with it. The square root of 0 is 0. Square root of 1 is 1. The square root of 4 is 2. Square root of 9 is 3. And the square root of 16 is 4. So I'm going to graph those 4 points. 1, 1, 4, 2, and 9, 3. You might notice this has a very similar growth pattern as a parabola. It's actually a parabola sideways. There's also this kind of thing down here. I'm putting that in dashed lines because that is not technically a function. So, depending on how you look at the square root and who you talk to, that's what it looks like, sideways parabola. I'm going to go ahead and erase those little dot parts. I want to make sure to clarify the points that I expect you to have on there. The locator point, shoot, that's the one that I forgot to have you do. That right there is the locator point. I knew I forgot something in that intro video. And basically you can think of that in terms of the sideways vertex. The domain is x has to be greater than or equal to 0. Range, y has to also be greater than or equal to 0. And this does not have any asymptotes either. Okay. Whoops, didn't. Cubic. I may be going out of order. I have some method to my madness, so don't worry about it. If I have negative 2, looking up at the table right now, negative 2 to the third power is negative 8. Negative 1 to the third power is negative 1. 0 to the third power is 0. 1 to the third power is 1. And 2 to the third power is 8. So I'm going to graph those 5 points. And then this starts to go very, very up and down. Those 5 points that I specified, those are the ones I would expect you to show. Although I will say with a cubic, sometimes those, you can't get them all in the graph. That point right there, that is your locator point. That's your HK. Your whole graph centers around that point. There we go. And people refer to that in different ways. My favorite from last year was that's the swoopy point, but it doesn't really have a name other than being the locator point. The domain here is all real numbers. Range is also all real numbers. Asymptotes, there are none. Even if it may look like it, those continue to go out left and right in both directions. And that's it for the cubic. I do want you to take note of these values right here, because as we show you that again, we know that these numbers were a number cubed and they fit on our graph over to the cube root. Those become the values that we want to use, because while there are many, many cube roots or perfect cubes, not very many fit on our little 10 by 10 graph. So we're going to go -8 that we got from the previous graph, -1, 0, 1, and +8. And I'm going to jump back, so that's what we're using for our x value. And because cube and cube root are inverse functions, cube root of -8 is -2, cube root of -1 is -1, cube root of 0 is 0, cube root of 1 is 1, and cube root of 8 is 2. So I'm going to graph those points. So go -8, and I'm going to try to do this without running into my editing things. -8, -2. I don't know if it made me do 0, 0, 1, 1. And oops, too far. So what you might notice here when you do these points is these 3 points are the same for the cube and the cube root, which is why it's really important to get these outer points that you of course cannot see on the other side. I missed it. Dang it. Hang on. There we go. Okay. Nope, should have just scooted it back over for good. So then I connect those very much in the same way as I did my cubic. And back again. Okay. So that's my cube root. That has a domain of all real numbers, range, all real numbers. We only use these specific numbers in our table because we knew they had perfect square roots. Sorry, perfect cube roots. And it's just easier to graph when you're dealing in whole numbers. There are no asymptotes. And once again, that point right there, 0, 0, our little swoopy point, that's our locator point. That is the HK that you will build the rest of that graph around as we start to do graph transformations. Next up is the rational, also called a hyperbola. If we just stick with the table and we do 1 over -1/2, or sorry, -2, we get -1/2. 1 over -1 gives us -1. 0, 1 over 0 is undefined. We cannot divide by 0. 1 divided by 1 is 1, and 1 divided by 2 is 1/2. So if I just graph those points, -2, -1/2, -1, -1. I can't do anything with 0. I know something weird is going on there. 1, 1, and 2, 1/2. That does not give me enough to figure out what this graph is going to look like. So I need to look at what's going to happen as I go further out on the x-axis and further back. So think about this in terms of our equation. If I go further out here, if x equals 3, my y value is going to be 1/3. If x is 4, it's going to be 1/4. 5, 1/5. I'm getting too close already. Anyhow, as I continue out 1/100th, it's going to get closer and closer and closer. As x is 1,000, it's going to be 1,000th. But it's never quite going to make it there. So this is creating an asymptote at the x-axis. It's going to happen as I go backwards as well. But we also have to figure out what is happening to, I'm going to put that asymptote because it's approaching it, but it's never going to touch it. So we can already list, we do have one asymptote at y equals 0, because that's on that's that horizontal line at the x-axis. So if we look at our values between -1 and 1 for x, we need to look at fractions. So if x equals 1/2, then I have y equals 1 over 1/2, which gives us 2. So my value there, 1/2, positive 2. Whoops. That's going to be the similar thing at -1/2, -2. If I do, if I do y equals 1 over 1/3, that's going to be 3. So basically what I'm looking at this graph is a similar thing. It's just going to get closer and closer and closer and closer and closer. But it's never going to touch that y-axis, which means I have another asymptote at x equals 0. And that's one of those things that we could also tell from the graph. So there's my asymptote at x equals 0. So the way I can tell that, not from the graph, I'm sorry, from the equation, is if I cannot put in 0 for x, then x cannot be 0, which doesn't always tell me I'm going to have an asymptote, but it's a pretty good indicator. And if I can't ever put in 0 for x, then I'm never going to get 0 for y. So there's nothing that I can put in for x that's going to give me 0 for y. So that is a value that that particular graph can never reach. So the domain is from, let's see, x has to be less than 0, or x has to be greater than 0. I can always also write that as x can't be 0. And I can write it in interval form too. For the range, same idea. Y has to be less than 0 or greater than 0. Or in other words, y can't be 0. So what you need to graph on these things. Make sure you graph the asymptotes in dashed lines. And then make sure you show these 2 points right here. Those are the specific ones. Those are the important pieces, and then make sure you actually draw this curve the best you can. It's a tricky one to do. The locator point is not actually on our graph. The locator point is where the asymptotes cross. Try that again. So whenever you build a hyperbola, that's what this graph is called, you're going to build it around your asymptotes. That's the first thing you're always going to graph, and that's going to make it easier to do. Alrighty, one more. Absolute value. This one is one of the easiest out of all the parent graphs. Absolute value means distance from zero. So everything going into the absolute value lines here is going to come out as positive, because the distance, whether you're 5 below 0 or 5 above 0, you're still 5 away from 0. So that's distance from 0. So -2 is 2 away from 0. -1 is 1 away, 0 is 0 away, 1 is 1 away, and 2 is 2 away. So when I graph this, 0, 0, those are my 5 points. Those are the ones you're going to graph when you, are the ones you're going to specify when you graph an absolute value. Although absolute value graphs are a lot less tricky because they are 2 straight lines. But do specify those points anyway. Domain is all real numbers. And the range is y is going to be greater than or equal to 0. For the simple reason that there's nothing negative on the parent graph. There are no asymptotes on this one. Locator point is, I can't write, it's getting too late for this. Locator point is 0, 0, as it is with every single other graph, parent graph. It starts to move around when that HK starts changing. But it's the vertex. So those are your parent graphs. Hopefully you got all those, and hopefully you didn't have an obscene amount of time left at the end of the period. And we will be, pardon me, transforming those graphs next class. So moving them around and all that goodness. So have a lovely day, and I will see you guys on Friday. Range. Whoop.